Okay, so we're in 13.2 now, and this is where we first start doing calculus that actually looks like calculus. I know in the last section I said this 13.1 was the first section where we do any real calculus, but really it was limits. And when most people think of doing calculus, they're thinking of derivatives and integrals. And so we're doing that here, but before we get into it, I want to talk about what a derivative is really used for and what an integral is really used for. There's kind of an unfortunate thing that happens when we teach Calculus 1 and Calculus 2, and it's a necessary thing, but I think it sets students up for the wrong idea about derivatives and integrals. We initially start learning the concept of a derivative by looking at slopes of tangent lines to a curve given by some function. And that's a very valid interpretation of the derivative when we are talking about functions of a single real variable. However, the concept of the derivative is used in far more contexts than just that limited scope of functions that we talk about in Calculus 1, and that is again functions of a single real variable. We talk about derivatives of multivariable functions, which we'll do in chapter 14. We really call those partial derivatives, so they're not quite the same thing, but they're very closely related. We're going to take derivatives of vector functions. In other courses, you can take derivatives and integrals of complex valued functions. And there's even more beyond that. So the concept of a derivative and the concept of an integral extends way, way beyond what you see in Calculus 1 and 2. And in the majority of those other contexts, there is no concept of a tangent line to a curve, because those functions, if they have a graph, may look nothing like a curve. Same thing with integrals. So, when we introduce students to definite integrals at the end of Calculus 1, we teach them that the definite integral represents the area under a curve. In this class, we're going to talk about a few different types of integrals. Here we're going to look at integrals of vector functions. In chapter 15 and 16, we look at double and triple integrals, we look at line integrals, surface integrals. Those things don't necessarily have anything to do with area under a curve anymore. Yet in Calculus 1, we sort of condition students to think that that's what an integral is. It's supposed to represent an area under a curve. And the truth is it only represents that in a very, very small slice of the functions that we actually can take integrals of. So what is a derivative actually for? And what is an integral actually for? Well, the key is also something that you talk about in Calculus 1. A derivative is a rate of change. And you know this already. It represents an instantaneous rate of change in a function, a change in its output over a corresponding change in its input. That concept is useful with any type of function. Looking at a rate of change in a function, whether it's a function of a single real variable, a function of multiple complex variables, or any other kind of function you can define, rates of change have meaning in all of those contexts. And so that's what derivatives are actually important for. The whole slope of the tangent line thing, in the long run, is not that important. It's the rate of change concept that's important. With integrals, what's the important concept behind an integral? Well, an integral is not the fact that it represents an area under a curve over some interval for a single variable function in the grand scheme of things, honestly, is not that important. What is important is that definite integrals represent net change in a function. So notice both concepts, derivatives and integrals, are about change. One is a rate of change, the other one is a net change over an interval. And you talk about both of those things in Calculus 1. Those are the concepts that make derivatives and integrals useful with vector functions, with multivariable functions, with complex valued functions, with functionals, which is it's a topic that we won't go anywhere near in this class. It's what makes those things useful, and it's why we can do calculus outside of the context of real functions of a single real variable. So now that I've spent about 5 minutes blabbing on about this, let's actually get into how we take derivatives and integrals of vector functions. So we want the derivative of any function to represent an instantaneous rate of change. Now, the limit definition of a derivative that you come up with in Calculus 1 encapsulates that perfectly, because again, what is a rate of change? It's a quotient. And what do we look for in that quotient? We look for a change in your output divided by the corresponding change in your input. So when we talk about vector functions, the input looks like a scalar, the output looks like a vector. So what we do here is we say, let's take two inputs that are very close together. Let's say t is one of them, and then if we add a very small number h to that value t, that's going to give us a different but very close input. The difference between t plus h and t is just h. That becomes our denominator. What is the corresponding outputs? Well, if I plug t into my function, then I get a vector, which we're going to denote r of t. If I plug t plus h into my function, I'm going to get a vector denoted r of t plus h. The difference between those two vectors is going to represent the change in that position vector for that function corresponding to the change in our input parameters here. Okay, so I think I'm pointing at stuff that's off the screen. Let's scroll up a little bit. So change in output over a change in input. Now graphically we can think of this in this way. So if r of t is a vector function that corresponds to a space curve, let's say c, here's the position vectors for r of t and r of t plus h. And again, remember, we always think of them as position vectors. So the difference between those two vectors, r of t plus h minus r of t, based on what we learned about subtracting vectors, would be a vector that has endpoints coinciding with the two terminal points of these two vectors here, this terminal point and this terminal point, pointing towards r of t plus h. We call that a secant vector. Same idea as a secant line that you learn about in Calculus 1. Now, again, remember the idea here is to turn this thing into an instantaneous rate of change. So if we're looking for the rate of change over this interval in our parameter from t to t plus h, this secant vector is giving us kind of an approximation for the instantaneous rate of change here at r of t. But as we see in calculus, if we can take the limit as this point gets closer and closer to this point, which is the same thing as taking the limit as h goes to 0, that little bit that we add to t, then that should give us an instantaneous rate of change. And we talked about how to deal with limits of vector functions back in the previous section, so this is something that we can technically do now. And that's how we define the derivative of a vector function. Notice the notation that we use is similar to what we use in Calculus 1. This is Leibniz notation, so dr dt, remember t is your independent variable, or r prime of t, either of those we use to represent that derivative. Okay? Now, let's try to make a little bit more sense of this, because again, remember, the numerator here is a difference of two vectors, so that would make it a vector. And we're dividing a vector by a scalar. Technically, we don't have an operation called scalar division. So what does this quotient actually mean? Well, down here, when I say r of t plus h minus r of t divided by h, what I really mean is that we're multiplying this difference by 1 over h, because scalar multiplication is something that we can do with vectors. So we're using this as shorthand, but this is really what we mean by that. Okay? Now, again, think about what the end result of this will be. If you're doing scalar multiplication, the output is a vector, and applying a limit to this vector as h goes to 0 is going to produce another vector. So the derivative, or r prime of t, is another vector, and here's what that would look like. Again, if we take the limit as h goes to 0, it's bringing this secant vector closer and closer, these 2 points closer and closer together. One thing that's worth noting here, compare this secant vector to this one. This secant vector just joins these two endpoints. This one seems to shoot right through that second endpoint, and why is that? Well, it's because it's not just the difference between these two vectors that we're looking at. We're scaling this vector by 1 over h, which means the vector is going to either shrink or grow larger, unless 1 over h is equal to 1, and then it won't change in size at all. But remember, we're multiplying that secant vector by a scalar, which is why it looks longer in this case. Anyways, as h goes to 0, this is going to shrink down to what we would call a tangent vector. And it's intuitively tangent to that space curve, r prime of t. We see that right here. Okay, so secant vectors, tangent vectors, there's your definition of a derivative right there. Okay, now, go on to the second page. Oftentimes, when we are looking for a tangent vector to a curve, this is a common thing that we need to do in this class. We're given a space curve, and we're told some point on that curve, and we're told, you know, find a tangent vector. That tangent vector could be r prime of t, like we see right here. But, you know, any scalar multiple of that would also be tangent to that space curve. It doesn't need to be this exact length or have this exact magnitude. And in most applications, it's really preferable for this to be a unit vector. It's preferable for that to have a length of 1. R prime of t is not necessarily going to automatically have a magnitude of 1. It can be lots of different things. So what we would like to do in many cases, once we've found r prime of t, we'd like to normalize it, which again, remember that means find a unit vector that has the same direction as r prime of t. And that vector ends up being more useful than r prime of t in a number of applications. So that's what we're defining here, the unit tangent vector. If we want the unit tangent vector to a space curve, this also applies to plane curves as well, at a particular point corresponding to the parameter t, then we just take r prime of t, which is a tangent vector, and then remember we divide that by its magnitude, which makes it a unit vector in the same direction. So this is the unit tangent vector. We'll be using that concept a lot in the remainder of chapter 13. Okay. Now, notice up until this point, we've really only been dealing with the concept of the derivative, the definition of it. We haven't evaluated any derivatives. And if you recall back in Calculus 1, when you first learn about derivatives, you're taught that limit definition. You kind of build up to it with secant lines and all that kind of stuff. And then you get that limit definition. And then you're asked to evaluate a bunch of derivatives using that definition. And it only takes a couple of examples to see that it's a really cumbersome and messy process, even for the really easy derivatives. That limit definition is not as useful for actual calculation, and that's why we derive all of these derivative rules. You know, the product rule, chain rule. We learn how to differentiate polynomials, natural logs, exponential functions, trig functions, the whole gambit of important functions in Calc 1. And then you don't use the limit definition anymore. We want to be able to do the same thing here. Unfortunately, we don't need to learn a whole new set of rules. It turns out basically everything that we learned in Calculus 1 about taking derivatives can be used here as well. And the reason for that is this. If you have a vector function, in this case a function in 3 space, but this applies to 2 space or n space or anything like that, then the derivative of that vector function, assuming it is differentiable, which means assuming the limit in the definition on that previous page exists, then finding that derivative is just a matter of differentiating each of the individual component functions. So if r of t is equal to this, f, g, h, then r prime is equal to f prime, g prime, h prime. And the proof of that is right here. It's really straightforward. I'm not going to walk you through this line by line. It's actually a good idea to read through this on your own and see if you can make sense of the steps. But the important thing to note here is that the component functions are functions of a single real variable. So differentiating them looks exactly the same as differentiating them in Calculus 1. So first example. R of t is this vector function, t squared cosine of t, e to the 2t. What would r prime of t be? And then we'll also find the unit tangent vector where t is equal to 0. R prime of t, finding that is just a matter of differentiating each of these with respect to t. So that the derivative of t squared is 2t. Derivative of cosine of t, negative sine of t. Derivative of e to the 2t, that would be 2e to the 2t. Okay. One thing I do want to point out here, The derivatives and the integrals that we do in this class, you should know all of your differentiation techniques, all of your integration techniques from Calculus 1 and Calculus 2. But in general, you're going to find that the derivatives and integrals are not quite as difficult as we make them in Calc 1 and Calc 2. And the reason for that is because practicing those techniques is no longer the focus of this class. Understanding how these things apply to vector functions, multivariable functions, and all that kind of stuff, that's what's important in this class. So we're not going to wreck you with like a horrible integral for the most part. That's not to say all of them will be easy, just not quite as difficult as you've encountered in Calc 2. So that's it. That's our derivative, r prime of t. Now let's take a look at that unit tangent vector. So what do I need in order to find the unit tangent vector at a specific value of t? Well, looking at our definition up here, we need r prime of t, which we just found. We also need the magnitude of r prime of t. Now, I don't actually need to take the magnitude of this thing as a function because we're only looking for the unit tangent vector at a specific point on that space curve. So what I'm going to do is start by finding r prime of 0, because I know I'm going to need that for my unit tangent vector. And that's just a matter of plugging 0 into each one of these. I see that I'm going to get 0, 0, 2 as a result. Okay? I know I'm also going to need the magnitude of that vector. Well, the magnitude of this vector would just be 2. And you can verify that directly if you want. It's no coincidence that it's the same thing as this component right here. If all of the components except for 1 in a vector is a 0, then the magnitude of that vector will be the absolute value of this one non-zero component. See if you can prove why that's the case. So what then would be my unit tangent vector? Well, I should be putting the arrow notation on all of these. So t of 0 is equal to r prime of 0 over the magnitude of r prime of 0. And we just found both of those. So this would be like 0, 0, 2 over 2. Remember, by dividing by 2, what we really mean is multiplying this vector by 1/2, which would give me this, 0, 0, 1. And again, you should be able to verify really easily that the result is a unit vector. It has a magnitude of 1. That should always be the case with this function. It can only produce unit tangent vectors, not just any tangent vector. Okay? Let's try another example. This time we're only asked to do one thing. We're asked to find our unit tangent vector, but this time it's not at a specific value. We're evaluating t of t. So we want this thing to be a function of t. Okay, so let's see if we can work that out. I know I need r prime of t. So in this case, I would have cosine of t I minus sine of t j, and then tk, the derivative there is just going to be 1. So I can actually just write that as plus k if I want. Okay? Now how about the magnitude? Well, if I want the magnitude of r prime of t, again, this time I'm not working with constants here. I'm working with functions of t. So that would be the square root of first component squared plus the second component squared. The fact that it's negative is not going to matter because squaring it will make it positive. So let's just say plus sine squared of t, plus that third component squared, 1 squared. Okay? Now cosine squared plus sine squared, I already know that's 1 plus another 1. This comes out to root 2. One thing I want to point out about this, in this example, the magnitude of this vector came out to a constant. That's not always going to be the case. It just so happened that I had a trig identity I was able to use here to turn this into a constant. But it's not too hard to see that with other functions here, that may not have happened. So this magnitude may come out to a function of t, and in some examples it will. Okay, don't be thrown by that. Now we need our unit tangent vector. Oop, this time it's not of 0 though, it's of t. Okay, so that would be equal to r prime of t over the magnitude of r prime of t, which we just found. Okay, so if I'm dividing by root 2, I know that's the same thing as multiplying by 1 over root 2. And my r prime that I just found was cosine of t negative sine of t 1. Okay, and I can leave my answer in this form if I want to. One thing I want to point out, my original answer was given in term of the standard basis vectors I, j, and k. Oftentimes we will leave answers in that form. Notice I didn't do that here. I put this in component form, and that's not for any particular reason. Technically, it's not incorrect to go back and forth between those two forms. It's just more often than not, for the sake of consistency, we won't. Okay, so don't be thrown by the fact that I did that. Second thing I want to point out, I didn't distribute this 1 over root 2 in here. I could have done that. It wouldn't have been a big deal, if I did that. But then I'd be writing a denominator of root 2 in all 3 components. It's just a tad less to write if I leave it factored out here. So don't look at an answer like this and think, well, it's unfinished, because it's technically not. It's okay to leave an answer in this form. Okay? All right. Moving on. So in Calculus 1, when you learn about derivatives, again, the idea is to find the slope of a tangent line. And then pretty soon after that, once you learn how to do that, you can find the equation of a tangent line to a curve at a specific point. And I kind of made this point at the beginning of this video, which was derivatives don't always give us tangent lines to curves, because the graph of a function may not represent a curve at all. However, in the case of space functions, in the case of vector functions, we do get curves. We get space curves or plane curves. So we can make sense of the tangent line concept here. And we're gonna talk about that now. So let's suppose that C is a curve, either a plane curve or a space curve, given by some vector function r of t. And then let's suppose that we also have some point P that we know of on that curve. Let's suppose that point corresponds to some specific parameter value, t of 0. So that, in other words, if I plug t of 0 into my vector function, it's going to take me to that point P. Or t naught, let's call it t naught. So if r is a differentiable function, if r prime of t naught exists, then we say that the tangent line to the curve C at the point P is the line that's parallel to that tangent vector, r prime of t naught, containing the point P. Okay, that's pretty straightforward. If we're going to define a tangent line to a space curve, this is kind of the natural way to do that. So let's look at an example. Here we want to find parametric equations for the line tangent to this curve right here, the curve given by this vector function at the point 0, 0, 1. First thing I want to do before taking any derivatives or anything like that is determine for what value of the parameter t would I get this point from this vector function. In some cases, you may actually need to write out all 3 components and set them equal to all 3 of these values. But in most cases, you can actually just figure it out by inspection. So again, notice my first component here is 0. I know that the natural log of 1 is 0, which would imply that t is equal to 0, in this case 0 plus 1. So it seems like t should be 0. Let's confirm that with the other 2 components. If t is equal to 0 here, I have 0 times, well, it doesn't matter because this will come out to 0. If I plug a 0 into 2 to the t power here, that would be a 1. So it seems like t equals 0 would give us this point. Okay, let's write that down, t equals 0. Next thing I need is my derivative, because again, we are looking for a tangent vector to this curve. So r prime of t. What is r prime of t in this case? Well, starting with the first function, natural log of t plus 1, its derivative would be 1 over t plus 1. Second function, t times cosine of 2t. I need my product rule for that one. I should get cosine of 2t minus 2t sine of 2t. That would be my derivative from my product rule. And then finally, the derivative of this exponential function would be the natural log of 2 times 2 to the t. Okay? Now again, we're looking for a specific tangent line, and we have a parameter value that takes us to the point at which we want to find that tangent line. So t equals 0 is going to be what I plug in here to get that vector that we want to use. So now we need r prime of 0. And this is easy because it's just plugging it in directly. So 1 over 0 plus 1, that's 1. Cosine of 0 is 1 minus, this would be 0, so I get another 1. Plug a 0 in here, that becomes 1 times natural log of 2, so natural log of 2. That's what I get. Okay, so this is the tangent vector that I'm going to use at this point on my curve here. Notice I don't need this to be a unit tangent vector. It would be fine if I found one, but that's extra work that's unnecessary. Any vector will work as long as it's in the direction that we need for that line. Okay, so now let's look a little bit more specifically at what we're after. Parametric equations for the line tangent to the curve at that point. Remember, in order to find an equation for a line, whether it's a vector equation, parametric equations, or symmetric equations, we need two things. We need a vector that that's parallel to the line. We have that here. And we need a point on the line. We have that here. The parametric equations would then be x equals the x coordinate of this point, which is 0, plus the x component of this vector times t, 1 times t. That just becomes t. Notice y is also equal to t in this example for the same reason. Z would equal 1 plus natural log of 2 times t. And those are the parametric equations that I can use for that line. Okay? We have a good amount more to do. We'll do that in the next video.